Certainly a great honor for me to be here at this birthday celebration. I was here, I guess, 50 years ago when we were in just Fine Hall. This is, I guess, Finer Hall as a graduate student. And so this is a wonderful occasion to come back here again. Of course, I have a great admiration for the honorees of this sort of mini conference, and I have to admit that the name Sinai has a particular meaning for me. In a Jewish tradition, of course, Sinai was the place at which the law was given to the Israelites, and Sinai was all, in some sense, the authority. In later days, when a question arose as to what is one supposed to do, or why are we supposed to do this, the answer was, well, this goes to Halacha Moshe Sinai. This is a law that goes back to Sinai. And I think it's not entirely inappropriate that our honoree Yasha was given the name Sinai, and of course his colleague David Ruelle is also very certainly I don't have to say this, how significant a figure he is in the area of statistical mechanics. At any rate, what I will be talking about is certainly not statistical mechanics. The relationship with dynamics will appear at some point in my talk. The title of the talk is Affine Representations and Harmonic Functions. We can talk about representations and basically this is more or less the same as talking about group actions. Except in different contexts, the different terms are used, and for us, they'll be interchangeable. The notion of representations arose in mathematics basically in considering representations of a group even on a finite dimensional linear space, and I may say already that an important notion in this representation theory is the notion of an irreducible representation. Namely one where you act on a space, but there's no proper subspace which is invariant under the action, and so you have a sub-representation. And we will actually be focusing on this, but in a different context. So there are various contexts in which one considers group actions or representation. It depends on their category. So we have, let's say, vector spaces. Let me write this as a linear space. And then when you add to the structure the notion of a bilinear form, you have a notion of a Hilbert space. H Hilbert space. Then we also have the notion of a measure space. Let's note that as the combination XB mu probability space. And that's where ergodic theory comes in, when you have a group acting on a measure space, preserving the measure. In each case, there's a certain structure which you're preserving, and then just simply a topological space, say X topological space. And each of these notions, you have the notion of something irreducible. Here you would talk about an irreducible representation. Here in the case of the probability space, it's not so common in fact, one doesn't use the term irreducibility, but the term that one uses is for an ergodic action, which means you can't find any proper subset on which is invariant. So here the term ergodic comes in. And in the case of a group acting on a topological space, the usual expression is a minimal subset or minimal system. Where no proper closed, well, usually it's a compact topological space for which the theory has been developed. And and a closed subset, which would be invariant, would also be a compact space, and so that would again give you a sub-representation. And so these are the examples of irreducibility in those contexts. I won't be talking about any of these, although these will come in. But the category in which I'll be interested in is a compact. Let's say this, compact convex spaces. I'll denote sometimes by CCS. So you have a compact topological space, and which is also an affine structure. In other words, you have the notion of convex combinations, and convex combination, you have a pairs of points or any finite number of points, but you can extend that to the notion of a barycenter. If you have a measure, let's denote by Q, is a convex set, and you have a measure mu belonging to M of Q, which will mean a probability measure on the space Q, then we have the notion of the barycenter of mu, which is the center of gravity, and which can be thought of as the integral. B of mu is the integral, sort of an abstract integral of x d mu x integrated over Q. And this takes the compact convex structure of the measures of Q to Q. So this gives us a map from measures of Q to Q, which is an example of a homomorphism in this category of compact convex spaces. Here, M of Q, M of any space. If G, this is perhaps an important notion, if G acts on a compact space X, then G acts, I'll call it affinely, on the measures on X, where we'll write G if mu is a measure on X, then G mu is another measure on X, which is defined by G of the measure of a set A under G mu is the measure of G inverse A. And so this is a natural induced action on the space of measures. This will come in at a certain point in our discussion. So now in general, one would like to know for a given group in some sense, all representations. Of course, there's no hope really of making this meaningful, but there is a hope of looking at irreducible representations. And in some cases at least, the general representation is going to be made up of, can be decomposed into irreducible representations. For example, it's well known, if you have a compact group acting on a linear space, that can be broken up into or at least on a Hilbert space with the structure, that can be decomposed into irreducible sub-representations. One perhaps doesn't think of it as often, but a general measure-preserving transformation of a measure space can be decomposed into ergodic transformations. The space can be decomposed into subsets on which the action is ergodic. So that's another situation in which the most general situation, most general representation is determined by, if you want to understand the most general representation, it's enough to understand the irreducible representations. Now this is not true in the case of general action on a topological, compact topological space. It cannot be reduced. It's not in any sense the sum or integral of minimal representations, minimal actions. At any rate, there's good reason to try to find all the irreducible representations, and this has been there's been something that people have worked on for a tremendous amount of work has gone on to this in the case of unitary representations. And it's an extremely difficult subject and very complex. And one of the interesting things about the category that I'll be dealing with is that you can, in many cases, put your finger exactly on what are all the irreducible representations. And we will deal with this topic in particular for one particular group, and I believe that much of what we say can be generalized to more general Lie groups. So we'll be talking about the PSL2. So G will be for at least this part of the discussion PSL2R, which I can also think of as the Möbius group of analytic automorphisms on the unit disk, which I'll denote by delta. And the first thing I'll do is give a nice example of an irreducible representation of this group, an irreducible affine representation of this group. Let me first make a remark. Given any group G, if I look at L infinity of G and think of it as the dual to L1, then for one thing I can talk about the weak topology or weak star topology on L infinity. And this is the topology of interest to us because, say, the unit ball or any ball, BR, equals a set of vectors in L infinity, let's call them Y, such that the norm of Y is, say, less than or equal to R. Then this is compact. This is compact. This is well known, and it's also convex. So it's an example of a convex set. And the group acts on it in a natural way where a function of G goes into, say, gamma f of G. We note it this way, where gamma f of G will be f of G gamma. I have to put this to the right in order that this be an action, so that if you can check that gamma 2 of f is the same thing as gamma 1 of gamma 2 of f. If I write it this way, if I did it the other way, it wouldn't work out. It wouldn't be really proper group action. So this is a natural way in which the group acts on functions, say on L infinity, and in particular the unit ball is an example under this action. So BR, if in this case, in the group case, so say the unit ball or any ball BR inside L infinity of G is CCS with the group action in that way. Of course, now because of the compactness, any invariant subset, for example, the BR will have irreducible invariant subsets. It will just because of the using Zorn's lemma. In fact, the intersection of of compacts is compact and non-trivial. So let me give an example of that in this particular case. Suppose let h of z be a harmonic function on the disk, on the unit disk, on which our group is acting on this by Möbius transformations. If you prefer, you can think of the upper half plane instead of the unit disk, and then it's easier to write down the transformations. Then W, if we think of W in the upper half plane, goes into, say, AW plus B over CW plus D with A, B, C, D real. So it preserves the real line, and so it preserves the upper half plane and the lower half plane. Well, provided the AD minus BC is positive, then the upper plane, F plane, will go into itself. At any rate, so I have this harmonic function on which the group acts. But it turns out to be a very useful thing to lift this harmonic function up to the group itself. So what I do is I define capital H of G to be little h of G of 0. Now there's a subgroup of G, K, which I call K, which is a maximal compact subgroup of G, which consists of rotations. Rotations about 0. And so this function h can really be thought of as a function on G mod k. And conversely, a function on G mod k gives you a function on the disk. Now, what are properties of this function? And that's where things become interesting. It turns out that you have integral equations rather than differential equations, which characterize these harmonic functions when lifted to the group. The reason is that if I look at the integral, well, first let's still look at h. H of k, say G prime of 0, k is the rotation element, and if I integrate this over k, so I'm rotating, I have some point G prime of 0, I'm rotating it, I get a circle here, and here I'm getting the average of that at the circle is the value at 0. So this is equal to h of 0. Now, harmonic functions are preserved by analytic automorphisms, so I can say I have I can replace h by h composed with g. So I now get the integral of h g k G prime of 0 dk is equal to h of G of 0. Now, think of h composed with G as a single harmonic function. And now here I can look at capital H, and this gives me the formula that capital H, this is just capital H as a function. Capital H is equal to the integral of kg prime acting on h of h with our notation what is meant by the group acting on h dk. Now let's take now the convex set, let's denote it by let me just arbitrarily do v sub, for any function, capital F, in this will be inside L infinity of G. A Vf is the smallest in G invariant compact convex set in L infinity. In other words, I take a function f and I take all its translates G prime of f, and I take the convex combinations of these and close that. So this is Vf. Now what can I say about VH when H comes from a harmonic function? Well, we have this formula over there. The functions G prime H are all inside VH. And these are the functions that generate VH. And I have that formula. So this formula would be good if I take different G's. I would also have H is still equal to, if I take a convex combination of, say, sigma alpha I K G I of H and integrate that with respect to K. This will again give me the function H. I've just taken a convex combination, say alpha I bigger than 0, sigma alpha I equals 1. This is a convex combination. I still get H. Now this is a typical element, well not quite typical yet, but inside VH. And if I pass to the limit, I get all the elements of VH. So the conclusion is that for any F belonging to VH, H is equal to K acting on this function F and integrating over K. I claim that this implies that VH is irreducible. Why? Because from any function in VH, I get back to the function H by convex combinations, which keep me inside the space. And from here, I get to any function in VH by acting on the group and taking convex combinations. So therefore, so that's the reason that this is irreducible. You can't find anything inside of it. Anything inside of it, you get back to H, and then you get all of VH. And if there's any question at this point, you should feel free to ask. So this is an example of an irreducible affine action of our group. Well, now there are lots of bounds. In other words, for every bounded harmonic function on the unit disk, there is an irreducible subspace of L infinity. You can also go in the other direction, and I don't want to take the time for that, but in fact, for if say V is any K invariant, any G invariant compact convex set in L infinity, there will exist some, because K is an amenable group, so acting on any convex space, there's always a fixed point, and it turns out there's a unique fixed point. There's a unique function, let's call it H, belonging to V, which is K invariant. And why there's a unique one? It turns out that in any affine representation of this group, there's a unique K invariant element. We may have time to explain that later, but right now you can take that for granted. And it turns out that H, which is since it's K invariant, it's a function on G mod K, and H in fact is H of well, let's say H of G is in fact H of G of 0 for some harmonic little h. So there's a 1-1 correspondence. So you have a 1-1 correspondence between the bounded harmonic functions and irreducible subsets of L infinity, of the group, infinity of this group. So your conclusion is, when we were aware of this, and when I say we, I should have remembered to say at the outset that everything I'm saying today is part of joint work with Elie Glasner and Benji Weiss.
So the eigenfunctions of the first
I'm sorry.
Other eigenfunctions of the Laplacian, which are not harmonic.
Right. So they tend not to be bounded, but what you do get are invariant cones,
Right.
and you can, I believe, take much of this theory carried over from compact convex sets to cones with a compact cross section, and I have a student who's working on that now. But so this is joined with Ellie Klausner and Benji Weiss. Okay, so we were remarking that, I was remarking that we have this 1-1 correspondence between this huge space of bounded harmonic functions and irreducible representations. This leads one to expect that there are going to be an enormous number of irreducible representations. And I thought at some point that I'd shown that there's a countable set, and the question is it a countable set or a continuum of irreducible representations? When I spoke to Kajdan about this, he said, oh, there must be a continuum. It turns out there's exactly one irreducible representation up to equivalence, and this is our main result I want to talk about. Of course, the irreducible spaces that you get in L infinity are distinct and don't overlap because of irreducibility, but it's a main theorem. Up to equivalence, this group, PSL2, has a unique irreducible affine representation. Okay, this is where dynamics is going to come in. Suppose you have G acting on, now G is a general group. Just don't like to change the notation. So suppose G acts on compact, let's talk about compact metric. Let's make it metric for simplicity, compact metric space X. There's a notion of a proximal action. This is a word that you'll find in your dentist's office about proximal cavities, but otherwise it's not such a common term. Anyway, the action is proximal if for any x and y in the space, there exists a sequence Gn in the group so that the distance between Gnx and Gny goes to 0. Now it's easy to see that if this is true for pairs of points, you can take any finite number of points and get them all to come together as close as you like. But first you start out with 2, get them together, and then you look where your third point went into, and then you get those together, and so on. But now it turns out that this is different from the following, which you might think as being the same thing, we say G acts strongly proximal. Action is strongly proximal if, well, I'll put it in the one formulation, which is in some sense most intuitively understandable definition. If for any point x in the space, any open set contained in the space, any epsilon positive, you can move, there is a G which moves most of the space into, oh, actually I don't need this, originally I was thinking of U as being a neighborhood of X, but it doesn't really have to be, so just this part. For any open set in X, oh, I'm sorry, we still need the little x, yeah, for any, and any epsilon, we can get all yeah, no, I don't, I'm sorry, I don't need the point. You can think of U as being a neighborhood of the point X, which it could be. We can squeeze most of the measure into this, most of the space into this open set. Now, what do we mean by most of the space? Well, you pick your measure, any measure that you like, which is going to describe most of the space, and you can squeeze that into the neighborhood. So that means there exists some G, so that the points, the measure of the set of points that move into U under G is bigger than 1 minus epsilon, where mu is a probability measure.
Quantifier on the measure. What point do you choose to measure?
So you have any.
Is this waiver? There is a measure.
Yeah, no, I'm sorry, I don't need this. Yeah, so I'm given an open set, and I want to move things into that open set. I say that I can move most of the space into that open set by some element G. So obviously this implies proximality. Excuse me?
This action is on a compact metric space. So far you haven't introduced the measure. So you're saying that for...
And because it's compact, so therefore that means you can get things as close as you like to any point. And well, that's already implicit here.
Every measure, I guess.
I think he means that for every measure there's a G.
Is this true for every mu?
I'm sorry, I don't...
I just don't know where mu is in your picture. G acts
for any mu... I'm sorry. I'm sorry. For any measure on the space. I'm sorry. For any measure on the space and any open set and any epsilon, I can move most of the space into that open set. It implies in particular that the action is minimal, because I can get any point, I can make the measure mu to be the Dirac measure at any point, and I can move that into any neighborhood, so that means that the action is minimal. Now it's clear that this implies proximality, because if I take 2 points, I take the measure, the average of the Dirac measures of those 2 points, and that can get into any open set. In particular, they can get within epsilon of one another. So that at least for discrete measures, if it's at least for discrete measures, proximality implies this stronger notion for that measure. But it turns out it's not the same as being for an arbitrary measure, and that's That's the notion of strong proximality. That for any measure, you can move that, you can squeeze that to be very small, to be essentially a limit of any. There is sequence of measures such that the sequence of elements in the group, such that applied to the measure, it goes to a point measure. That's essentially what this is equivalent to, and it's another formulation of the definition. That in the orbit closure of any measure includes point measures. Now, an example of strong proximality. A simple example of strong proximality is, e.g., our group PSL2 on S1, the boundary of the unit disk, the way the Möbius group acts on the circle. Well, if you take an element that takes the center to very close to the boundary, so it takes this geodesic to something like this here, which means it's going to move all of this, or rather all of this, into this small space. And any measure that you have, it'll also take some. Again, if you move it close enough, it'll take everything outside of some small arc into this small arc. And so that's pretty clear that makes it a strongly proximal action. Now the important thing is that a theorem, a proposition, call this proposition, if G acts on X strongly proximal, I'll just write it this way, then the induced action of G on the measures of X is irreducible. Now, why is that? If I have, well, we can think of this situation here. If I have here an M of X, I claim the action on all the measures here is irreducible, because if I have any measure here, I can squeeze that into a point measure, and then I can squeeze it, in other words, in the closure of that, I also have point measures, and because of this property that we spoke about before, I can get any point measure on here by looking at the orbit closure of the G action. And once I have all point measures, by Krein-Milman, or any way you want to look at it, you can get all measures. All measures are basically convex combinations of point measures. And so I can get all measures, and therefore from any measure I can get all measures, and therefore it's irreducible. So that's one way of getting irreducible actions. So besides this discussion of harmonic functions, you can also get them by taking a strongly proximal action, which, for example, is here, and therefore the measures on this form an irreducible CCS. But in some sense, the converse is also some form of converse which is true. If G acts affinely and irreducibly on a compact convex set Q, then the induced action, now if it acts on Q, it'll act on the extremal points of Q. The extremals don't necessarily form a closed set, so let's take the closure. And the action on, let me denote it as the extremals of Q closure, is strongly proximal. Okay, I won't indicate this. I'll just say that for this you use the barycenter map, and you can see why. From the irreducibility on Q, the the action on the extremals has to be, you can move anything to any point, basically. Okay, now another fact, general fact. There exists a universal, well, let me introduce another notion, which the notion of a homomorphism in any category. You can talk about a homomorphism or morphism between one space and another space, where there's simply a map which preserves the structure, whatever category you're in, and is equivariant. In other words, pi of gx is the same as g pi of x. And we call it a factor. We say that y is a factor if pi is onto. Now it's easy to see that a factor of an irreducible Q, I just denote the space, but I mean an irreducible, I have an action of G on Q, which is irreducible. So a factor of this is again irreducible. And this is true in all the categories. If you had something invariant, inside, say Q, you have Q to Q prime, and something invariant here, you would lift it back to Q, and that would again be invariant, and because of the equivariance. And so this is an important fact, very simple. Now, a phenomenon which you have with affine representations, which you don't have with linear representations, that it's possible for one irreducible representation to have as a factor another but distinct irreducible representation. This is not true in the linear case. If I have, say, V going to V prime, V prime an actor, a factor of V, then in order for this not to be equivalent, I must have a non-trivial kernel. But the kernel would again be invariant, and so then this could not have been irreducible. So the irreducibles in the linear situation have no connection with one another. In the case of our affine representations, it's very possible that that one irreducible has as a factor another irreducible, and moreover, and here, because of the equivalence between irreducible affine representations and strongly proximal representations, it's very easy to see that if I have two strongly proximal spaces, x and y, then I look at x cross y. So I have this, say, x cross y, and I take a minimal subset inside here, then again a minimal invariant subset inside x cross y. And if this was strongly proximal, so I can take any measure here, we'll go into something which has a point measure down here, so it's somewhere here, but then I take the strong proximality of y and get that to be a point measure, and so therefore inside x cross y there is some z which is strongly proximal, which maps onto both x and y. So any two, well, lifting this up to convex sets, you get that any two irreducible convex sets are factors of a single irreducible affine. But more than this, what you can do, and this is by kind of a hand-waving argument, there exists a universal strongly proximal action. And let's denote that this is for any group G, pi for proximal, and the space of measures on pi g, which called qg, is the universal irreducible affine for g. Now, what do I mean by universal? Universal means that everything else is a factor of it. So not only can you get something to be to factor on it two irreducibles, but you can get something to map onto every irreducible. Now, the pleasant situation, the pleasant fact in this theory is that for many groups, we know we can identify what is the strongly proximal, the universal strongly proximal action. And I think it's, I haven't really worked out the details, but it seems to be true for all Lie groups, connected Lie groups. In particular, it's true for, well, it's certainly true for groups of matrices, and in particular, what is the strongly proximal space for our group, the special linear group? In general, if P contained in G is amenable. Amenable means that every action, that every affine action has a fixed point. I mean, that's one way, that's one characterization of amenability. And by the way, obviously, if a group is amenable, then the universal, then an irreducible affine is just a point. And that's going to be the universal one for the amenable subgroup. And now suppose, and if G mod P, this is a space on which G acts. If this is, well, let's assume it's amenable and co-compact. Then this is a compact space on which G acts. And if this action is, if this is strongly proximal, then it is, then G mod P is the universal strongly proximal space. That's quite easy to show. So, for example, in our group in PSL2, the triangular subgroup ABD0 is amenable. It's a solvable group, and it's amenable. And the quotient space, called this P, parabolic, P for parabolic, and G mod P is essentially the projective line over R, or it can be identified with a circle. If you look at it as a Möbius group, then P fixes a point on the circle, and G mod P is basically the circle. So the circle, the boundary, is exactly the universal strongly proximal space for our group that we're looking at. And therefore, the set of measures on that space is the universal irreducible affine space. Well, this is far from solving the problem, because it may have many, many different factors. So and this is where some analysis comes in. So theorem, if M of S1 has a homomorphism to some Q, then either, and here we're talking about G is our PSL2. So if we take this space of measures, which is a compact convex, if this has a homomorphism to any other, onto any other compact convex set, then either Q is just a point, or the map is 1 to 1. Let's call this pi, or pi is 1 to 1, which means that this is really equivalent to this. And so this is really the statement that we're making, that since this is a universal, every other irreducible is a factor of it. And if this is true, then it's either trivial or this is 1 to 1, which means that this is the unique, non-trivial, irreducible representation for our group. Let me just say that if we were dealing with in 3 dimensions, if we were looking at the PSL3, then it turns out that the universal strongly proximal space is now the flag space on flags, in other words, lines and points and lines in 2-dimensional projective space. And so therefore, it has non-trivial factors, and so there are at least 2, one has 2 irreducible actions for that group. But it's not. We haven't been able to determine yet whether those are all.
Are they both strongly proximal? Are those 2 actions both strongly proximal?
I'm sorry, I don't.
Sorry, the 2 representations in the 3-dimensional case, acting on S2, are they both strongly proximal? One of them I understand. Which is strongly proximal. Is the other one is also strongly proximal?
In the 3-dimensional case.
I'm sorry. What's your example?
The first one would be Mobius functions on the 2-sphere.
If I just rotate, then that's obviously not proximal. In fact, the opposite of proximal is distal. And, that's even more so. Yeah. Okay, so so we're dealing with this, and let me quickly indicate what that depends upon. In general, if we had such a homomorphism, then if I look at the affine functions, which is something which is well defined, these real valued functions which preserve the convex structure. We have a map from affine. This would give us a map from the affine functions on Q to the affine functions on the measures of S1. Now the affine functions on the measures on any space. This is basically the same thing as the continuous functions on the extremals. Obviously, an affine function gives you a continuous function. Moreover, given a continuous function on a compact space, you can extend that to be an affine function on the measures just by integrating. So, given such a map, if we have such a map, then this equivalent to C. We have a map from affine functions on Q to continuous functions on the circle. Now this family, because this is invariant under convex combinations, we would have something continuous functions invariant under convex combinations and invariant under the action of the group. So from the convex combinations we can go to linear combinations, and we would end up with a non-trivial module, you might say, of continuous functions. We end up with, say, let's call it L, as a linear space, closed linear space of functions contained in C of X, C of S1, which is invariant under the group. Now, just take another minute or two. There is a property which is sometimes holds, which we call linear Stone-Weierstrass property, that such a that if I have a linear subspace of the continuous functions on the space X, and which is invariant under the group, then that's already everything, or that it's dense if I don't insist that it be closed. And that would, if this would be everything, that would finish the argument there. If that map has to be all continuous functions, then that means that that this map pi is a one-to-one map. Well, it turns out that the action on the circle has this LSW property. That is, if I have a bunch of functions on the circle, which are invariant, it's a linear space, and it's invariant under all the Möbius transformations, then it has to be dense in the set of all continuous functions. Now, one way to see this, if I start out with a function, all of whose Fourier coefficients are distinct from 0, then just by linear, sort of a Tauberian theorem, or elementary harmonic analysis, you can see that you get basically you get arbitrarily close to all continuous functions. So what if you have some coefficients that are equal to 0? Well, we have a bigger group. We don't have just rotations. We can change it by other Möbius transformations. In particular, say z goes to z minus t over 1 minus tz. That's a Möbius transformation which preserves the circle. And here you can take any t less than between 0 and 1. So this one parameter group of transformation which you can also apply. And it turns out that these Fourier coefficients being analytic functions of t, it turns out that for any particular Fourier coefficient, there's only a countable number of t's for which this can vanish. So therefore, for all n, you can find some t for which none of them vanish, and then you can work with that and you finish the argument. Okay, thank you very much.
Any questions?
Is there any condition on G? Is there any condition on G such that there exists a unique, strongly proximal irreducible representation?
That's a very good question. Yeah, and that's the same thing I think as saying. I think it's the same thing as saying that there's basically a unique, strongly proximal action which has this LSW property, and I don't know the answer to that.
Any more questions? Comments? Okay, thank you very much.
Okay, thank you.
We will be here until 7 minutes.